Lecture 3.5 Stellar Classification. In a previous lecture, we went over the stellar classification scheme that was finalized by Cecilia Payne. O stars being the hottest stars, M stars being the coolest stars. Also, as a review, we talked about the types of spectral lines that appear in different stars. The hydrogen-Balmer lines, which stand out as the sequence of lines that crowd closer and closer together as you move out into the ultraviolet part of the spectrum, show up strongest in A stars at a temperature of around 10,000 Kelvin. Neutral and ionized helium lines show up strongest in O and B stars. Calcium-2 lines show up strongest in G stars, so G stars like our sun. There's a pair of these lines out in the violet part of the spectrum that are very distinctive in G stars. And neutral sodium lines show up in K and M stars and weakly in G stars. In addition to this broad spectral classification, O, B, A, F, G, K, M, astronomers have also developed subclasses to provide finer distinctions on the temperature of the star based on its spectral class. So, for example, B stars are subdivided from 0 to 9. So a B0 star would be the hottest, and then B9 would be the coolest in the B range. And then right after you go B0, B1, all the way up to B9, then it starts at A0, A1, A2, all the way up to A9, and then F0, and so on. So here's a way of looking up what the temperature of a star of a particular spectral class is, given its subclass. So for example, a B0 star would have a surface temperature of about 29,000 Kelvin, whereas a B9 star has about 11,000 Kelvin. Our sun is about a G2 class, and so we see that's right around 5,800 Kelvin. This plot also shows some other more recently added spectral classes, L and T stars, which are very cool objects, but we'll not worry about those right now. These temperatures, by the way, are for luminosity class 5 main sequence stars, and we haven't defined what that is. We will in the next slide. In addition to classifying stellar spectra based on the relative strengths of the spectral lines, we can also classify them based on the width of the spectral line. So here's 3 spectra. These are negative images, so these white lines here are actually absorption features, so they're really dark. So this top spectra shows a series of spectral lines with fairly narrow lines. As you go to the bottom spectra, they get a lot broader. So this line is a lot broader than the one at the top. So we define the luminosity class as a measure of the width of the spectral line. Class 1 stars, Roman numeral 1 stars, have the narrowest line. Class 5 stars, or class 6 stars, have the broadest lines. Spectral line widths are largely determined by pressure broadening. So pressure broadening occurs when a gas of atoms are packed together tightly so that the electric field of one atom will influence the energy levels of another atom, and that will slightly shift what the wavelength of the absorption or emission features are from the atom. So stars with broader lines have higher pressure. Higher pressure translates to higher surface gravity. So this is a result of hydrostatic equilibrium, which we'll talk about later in the class. But basically it says that in order to support the layers of an atmosphere, if the surface gravity is stronger, you need larger pressure to support those overlying layers. So anyway, higher pressure translates to higher surface gravity. Higher surface gravity translates to a smaller radius of a star, assuming that the temperature is constant. And for a given temperature, larger stars are more luminous, and we saw that before. That was a result of the Stefan-Boltzmann law. So the luminosity of a star is equal to its surface area times the flux given off by the surface of the star, sigma t to the fourth. So for a given temperature, if you have a star with a larger radius, you'll also have a larger luminosity. So there's this logical chain that connects the luminosity of a star to the width of the spectral lines. And it's like somewhat involved to kind of prove all this. We're just going to kind of state it as a fact and then move on. So this is a summary. Luminosity classes, again, range from 1 to 6. Luminosity class 1 stars are called supergiants. They're the largest stars that we know about. And they have very, very narrow widths because, again, there's very little pressure broadening because the surface gravity is so low, because the stars have been kind of bloated out to such a large radius. Luminosity class 2 stars are called bright giants, 3 giants, 4 subgiants, and then luminosity class 5 stars are called dwarf or main sequence stars. So our sun is an example of a luminosity class 5 star. And we'll talk more about this later in the class. Class 6 are called subdwarfs, and they again have the widest spectral lines. So again, if we go back to the sample spectra, we see that this top spectra is from a supergiant star. It's physically larger and more luminous than the star from this bottom spectra. This is a main sequence star. It's a dwarf star, and it is smaller and less luminous than the one at the top. Notice that all three of these stars have the same spectral class and thus the same temperature. But they have different luminosity classes, which means they have different radii. Okay, you will be doing an activity where you classify different spectra based on a catalog of known spectra. So we'll be using results from a paper published in the Astrophysical Journal back in 1984. This is a library of stellar spectra, and we're going to go through this very quickly. This publication shows a sequence of spectra with different classes and subclasses for different luminosity classes. So this example, these are all main sequence stars, or in other words, luminosity class 5 stars. It starts with an O5 star, so this is the hottest star in the sample, and it goes down to class O 9.5. So this one down here is slightly cooler than the one at the top. And what you can see, first thing you might notice is that in all of these O stars, the spectrum is increasing. The intensity of the spectrum is increasing as you go to shorter wavelengths. This should make sense based on what you know about blackbody radiation. So very hot stars like O stars are emitting most of their radiation in the ultraviolet part of the spectrum, and they're also emitting more blue light than red light. So it makes sense that these hot stars, the spectrum would be sloping up to smaller wavelengths. Here's an example of B spectra. So you can start to see, even in B stars, the presence of the hydrogen-Balmer lines right here. You don't see those as much in O stars. They're much weaker. Here are examples from A stars. So A stars are where the hydrogen-Balmer lines are the strongest. So you can see that they dip down the farthest in A stars compared to other spectral classes. What one does to classify a star is to kind of look for these kind of broad features, whether the spectrum is sloping up to shorter wavelengths or up to longer wavelengths. You're looking for the spectral patterns of particular elements, for example, the hydrogen-Balmer series. But then you're also looking at the relative ratio of line intensities. So, for example, you might look at these two little lines right here in this F star. So this one right here is the H alpha line. It's fairly strong. This other little guy is a little bit weaker. As you go down to cooler and cooler stars, though, these two lines are starting to have about similar line strengths. And so by looking very closely at the ratio of pairs of lines, you can kind of pinpoint exactly what spectral subclass the star belongs to. Another thing you might notice is here in an F0 star, the Balmer lines are showing up fairly clearly. There's not a bunch of other spectral lines kind of messing it up. As you go down to cooler stars down to F9, those hydrogen Balmer lines are getting weaker, and you're getting a lot of other spectral lines present. And so again, by kind of looking at subtle details like that, you can get a very accurate classification of the star. So here's a G star. Our sun is a G2. So this right here is probably a pretty good approximation to what our sun spectra looks like. These two lines right there are the calcium, the ionized calcium lines that we talked about before. Here's a K star. Notice that we're shifting the bulk of the radiation to now longer wavelengths. So these are going to be kind of reddish stars with more of the light coming out in the red part of the spectrum. And M stars, that's even more pronounced. So again, not as much light coming out in the blue, a lot of the light coming out in the red. And notice in M stars, these coolest M stars, these M5 stars, there's a lot of absorption due to molecules that are forming in the outer atmosphere of the star. Here's an example showing the same spectral classes, A1 through A9, for a supergiant, a luminosity class 1 star, and a main sequence star, a luminosity class 5. So you can see the widths of these luminosity class 5 stars are much wider than the spectral lines for a supergiant luminosity class 1 star. All right, here's a summary of everything that we were just talking about. Talking about the different kinds of spectral lines that are present in the different spectral classes. Oh, by the way, I did forget to mention that there is another subclass of star we haven't talked about called a Wolf-Rayet star. These are extremely hot stars. The distinguishing characteristic of them is that they show emission lines in the spectra, not just absorption lines. So here's an example of the spectra of a Wolf-Rayet star. You're seeing emission now instead of absorption lines going down. So these lines are going up, not down. So here's a photograph of a Wolf-Rayet star. This star has recently blown off a lot of the outer layers of the star, and so you're seeing deeper in to closer to the core of the star, and that's why these objects tend to be much hotter than typical stars. These stars are mostly all in the dying phases of their life. They're getting ready to either explode as supernova or something else. Okay, so that's it. We will talk about radiative transfer in the next lecture.